I'm here to talk about artificial intelligence, which is the buzzword. And I'm going to start with this slide. And it's interesting because it is now 70 years old, New York Times story. And in fact, the title is The New Navy Device Learns by Doing. Okay. And it is a pointer to what we all know is that the media sometimes has a tendency to get science stories wrong. And so there's a quote here, which is, it's interesting because this was ONR must have funded perceptron work of Rosenblatt. Rosenblatt is like the founder of this field, which eventually today is what we call deep learning. But this was a single layer perceptron. But the point of this story is really that there were very, very exaggerated hopes of what could be achieved based on that first demonstration, which was, is the line horizontal versus the line vertical? And yet there was this hope that from this we would be, the brain is designed to remember images. Later, perceptrons will be able to recognize people and call out their names and instantly translate speech in one language to speech or writing in another language, it was predicted. So you kind of can do that now, but it took 70 years, not 5 years. Okay? So, okay. So I want to start by saying what's been responsible for current AI successes. So big computing and big data, these are the most important ones. And here I want to refer to this example going back to, now it's 20 years, Hans Moravec. Hans Moravec was a professor at CMU, and I was very influenced by him because he took great analogy from the development of biological intelligence into artificial intelligence, and he tried to do a calculation of what's the computing power of the human brain, and when can we have devices, computing devices, which would have comparable computing power. So here is this chart which he produced sort of about, it's 20 years ago, right? And on this chart, on the x-axis is time, so 1900, 1920, and so forth. And then on the vertical is computing power in millions of instructions available for $1,000. And you have various computers of the era. And assuming Moore's law, there's an exponential plot. So assuming Moore's law, you get some prediction. And from that, you got the result that in about 2020, we might imagine computing power comparable to a human, the human brain. So, and of course, it's 2018 now. So, in fact, it's kind of interesting to note that the computing power today is now available, which is comparable to what we have in the human brain, certainly if you allow a cluster of computers and so on. This was not so when we go back to the early days of AI. When people were studying this problem in the 50s and 60s and 70s, they were trying to make do with devices which were much, much slower in terms of computing power. We always talk about Moore's law forward, right? We say that there's a factor of 10 every 5 years. Okay, which means that every 30 years there's a factor of million. Okay, but let's work backwards. That means that 30 years ago, computing was 1,000,000 times less. And that's the context in which people like me started in the field. We had to work with computers which were 1,000,000 times slower. So we naturally had to make lots and lots of compromises, simplifying assumptions, and so on and so forth. And as a result, we did not make so much progress. Now we don't have to make those compromises anymore. It's a different matter that in terms of power consumption, we still are way off compared to where biology is, because the human brain takes like 20 watts, and our computers, these data centers are enormous power hogs. And that is an issue when you're talking about autonomy, but we won't focus on that. It's also interesting to talk about intelligence as a biological process. So let's think about this in evolutionary time. So for the first multicellular animals which could move around and which had some perception arose about 550 million years ago. So about 550 million years ago, you have these first animals that can move, and they can see and they can move. And that gave them an advantage, right? Because you can find food in different places. You can go to where the food is. That's great. Then you have predators and prey. So that causes an arms race, which causes both the visual system to develop as well as camouflage, techniques, armor, and then techniques for breaking armor and so on. So this big evolutionary jump which happened in the Cambrian era, some people attribute it to the development of perception and locomotion together. And then it continues, and then if you come to the last 5 million years, that's when we sort of have the first hominid line. And the interesting development there is the development of the hand. The development of the hand, from the apes to humans, the development of the opposable thumb. And there is very good evidence that, in fact, it was the development of the hand that drove the development of the brain rather than the other way around. That we had now capabilities, and we got some benefit in terms of being able to manipulate, and that gave us an incentive for having bigger brains. Finally, if you come to the last 50,000 years, that's when you have modern humans, language, abstract thought, etc., etc. So in the history, so this is why my talk is titled "The Sensorimotor Road to Intelligence." That means that for most of the 500 million years, it was really in the sensorimotor stage. And I really do believe that when we replicate intelligence, we will have to somehow follow this order, or at least large parts of this path. We can't get to language understanding without a grounding of language in the body and the physical world provided by these early stages. With this background, with this philosophical background on intelligence, let's turn to what are the big successes in AI today. So I already mentioned big computing and big data, and those are real, essential, and we could not do without them. And these are necessary for biological intelligence as well. Then we have big annotation and big simulation. And these are peculiarities of the way artificial intelligence has evolved, and I believe that in later generations we'll have to find an alternatives to this. So let me explain. So let's take one of the most visible successes, which is the success of DeepMind's at beating the human Go champion. And there is a subsequent program called AlphaGo. So this is a setup which people are very impressed by this accomplishment, right? Because Go is regarded as, earlier it was regarded as just so difficult that computers would not be able to conquer Go for some time to come. Chess was conquered in the late 1990s, right? Go is very recent. But I would argue that there are characteristics here which are quite special. The characteristics here are that the rules of Go are very precise, so therefore we can create perfect computer simulations. So the program can learn by self-play with millions or billions of examples. Now this is not something available in real life. In real life, we have to learn from very, very few examples. You cannot have these millions or billions of trials. So the techniques that have been developed in this setting, I would argue, are not going to immediately solve the problem of intelligence in general. It's a very, very special setting. Just like what happened with chess. It was an impressive accomplishment, but it did not scale to the rest of intelligence. What we have to deal with is the complexity of human behavior and so on, and that's going to take some time. So I'm starting my talk by saying that we have had enormous advances in AI, but there is a very long way to go, and I don't want people to think, okay, in 3 years we are going to solve this problem. No such luck. So the title of this is From AGI to AGI, where one AGI is what people call artificial general intelligence. That's what people are afraid of, that will computers get to the point will they decide that is it worth keeping the humans around as pets or not? right? That's that notion of, that scary notion of artificial general intelligence, which you see, the dystopian version you see in movies and Terminator and all the rest. Okay, but there is this other version of AGI, which is what we have, which is what I call artificial gamer intelligence. We can do these games, but there's a big gap. Okay, so now I want to take you on a journey of how we should be thinking about intelligence. I think it's very important to think about intelligence in this style of embodied cognition, where you consider vision or perception broadly. Perception means vision, audition, touch, all the senses. Motor control, which is acting in the world, and then language and abstract thought. And there are these great examples. There's this great example of in biology of this creature called the sea squirt, which for some part of its life it moves around, and then it has a brain and it uses the brain. Then there is a part of its life where it becomes like a plant. It's attached to a rock and it stays there. Once it gets to that stage, it actually digests its own brain and vision system. It has no value for it anymore. And the joke in academia is that this is what tenure leads to. Once you're a tenured professor, you have no more need for your brain. Okay, but there is a deep point here, which is that trees, for example, if they had sophisticated vision systems, they wouldn't get any advantage out of that. They could discuss poetry. Redwood trees could discuss poetry with each other, but they would not give them any advantage. It would not be worth the metabolic cost. So what are the major successes of deep learning? They are in computer vision, particularly in recognition, speech recognition. I mean, if those of you who have dealt with, you call up AT&T and you have some customer service kind of thing, and how painful those used to be in the past compared to the accuracy today. Machine translation, this has been say English to French or whatever, and then game playing. I think these are the major successes, which of course means that there's a lot of stuff which is left outside. I've already mentioned game playing. I want to say a little bit about machine translation and the way it has been achieved and the way it is different from the way humans achieve it. Humans translate by understanding what's being said and then representing it in the other language. Machine translation systems that we have today, they operate in a very different style. They are sequence to sequence. So you imagine that you're getting a sequence of words in English, which you're trying to convert to a sequence of words in French. And and the way it is done is by lots and lots of training data. So you have lots and lots of examples of text which has been aligned, which is English text and French text. So you sort of absorb symbols in English and you produce symbols in French. And these systems cannot really be said to understand the language or the text. They are merely converting symbols from one to the other, sort of like this Chinese room argument that John Searle, the philosopher, gave. So it's great, it's useful, it's very practically useful. And companies like Facebook and Google are providing you this service, and this is great. But I would argue that there is a great frontier of understanding natural language which is still open. Speech recognition, again, is a similar problem. It's sort of like this sequence to sequence kind of problems, and these have been very effective. That said, I'm going to focus most of my talk on computer vision because that's my specialty. I want to give you a little bit of background on how these ideas that have been so enormously successful today, how they came by. And these are examples of synergies in science. In science, often great ideas emerge in many, many different places, and then people pick on them in ways that the original inventors or scientists may not even have dreamt of. So there was work done by Hubel and Wiesel. These are neuroscientists who actually won a Nobel Prize for this discovery in 1981, who found cells in the brain, kind of in this area, the corresponding area. I mean, they did these experiments on cats and monkeys, not on humans, but There are cells which respond to orientation like 45 degrees or vertical or horizontal, and different cells respond to edges or bars at different orientations. So they discovered these kinds of neurons. And then they found that as you moved up the visual system that you got neurons which were sensitive to more and more abstract concepts, such as, so initially it might just be lines, but later on it might be there might be neurons which respond when you see a dog or a face or even the face of a specific person. Now, based on those ideas, people developed neural networks. So there's a work from someone called Fukushima. And what he was doing was really just taking the kinds of ideas that people like Hubel and Wiesel had developed, emerging from experiments in neuroscience, and building artificial neural networks from that. So there will be layers of cells corresponding to the different layers of a human or primate visual system. And the later stages would correspond to recognizing more abstract things like dogs and cats and so forth. And he said that there would be cells which would be like filters. These would be the so-called convolutional layers. And then there would be layers which are doing pooling, which is taking the average over some part of the visual field. So this was Fukushima's idea going back to 1980. This is a paper in 1980. In the 80s, techniques for training these neural networks were developed. And the idea was that you have lots and lots of examples. So you have example images and labels. So there's an image and there's a label saying that this is the digit 5. There's an image and there's a label saying this is the digit 7. And you have your neural network and it's going to give you outputs, and they will usually not be right. And what you want to do is to change the weights of the neural network such that it starts to give answers which are more correct. And that technique is called backpropagation. And the mathematics for that was worked out around then. And then systems were developed back in the 80s by Jan LeCun is the person who developed this convolutional neural network training style. And they were quite effective for applications like reading checks and so on. But they were not being used generally. And why? So let's think back. We are now talking about 30 years ago. So the kind of computing power you had was pretty limited. So therefore, what you could do was very limited. And these techniques really are big data hogs. They needed lots and lots of examples in order to be effective. So now we have to go fast forward to the 2010s. And you have now much faster computers. In particular, GPUs have become available. And big data sets like ImageNet have become available. And so that led to this breakthrough from Jeff Hinton's group in 2012, where they showed that these networks gave error rates significantly better than those of more conventional techniques in computer vision. So that made the whole field sort of sit up and say, okay, what's going on? Let's find out. So I'm going to give you an example of work from my group, which is RCNN, and Behzad referred to this. So this was aimed at taking this kind of neural network technology and applying it to the task of object detection. So we want to say in an image, what are the objects in there, and also mark where the object is. And in fact, this was research funded by the Muri that Behzad was sponsored. And we can do that. And we found that we could do it much more accurately than with pre-deep learning techniques. This area has subsequently led to great advances. Now a lot of the work, the cutting edge work in object detection happens in companies. And it's because they have the access to the biggest amounts of data and compute. So this is work, the mask RCNN system is out of Facebook. And here are some results. So what these different colors show is what the system thinks are are particular objects like humans or elephants or umbrellas and so forth. And I think, and here's another set of results. And these are, to me, extremely impressive results. Because 5 years ago, if someone had asked me, would computer vision get to this point? I would have said no. I would not have expected results of this quality emerging in around 2017. If 2012, if somebody were to take a bet with me on this, I would have said no way. Okay, so this is fantastic. I think that this is great, and I'm now going to take the approach that what remains to be done. So in the rest of my talk, I'm going to focus. I want to acknowledge the successes and then move on to what needs to be done. So what can't we do? If we look at this image, this is very flat, right? So this is it's just sets of pixels are being labeled as this is a chair, this is a dog. These are not objects arranged in three-dimensional space. Whereas what do we want to do? We want to perceive objects as having 3D shape. We want to think of everyone here as there's a person sitting on a chair, and some people are close to me and some people are further away, and so on and so forth. And that's the kind of conception we have in our head when we look at an image. So it's not just like this flat pattern. Now, what are the advantages of that? We clearly get some benefits from knowing about 3D, because we can reason about 3D when we want to move around in some space. We can talk about what use are these objects. If we want to manipulate these objects, how are we going to do that? So we need object-centric 3D. So we need to not just say this is a chair, but we want to say this is the shape of the chair, how far away it is, and I want to say this for all the objects in the scene, right? How are we going to do this? So I'll turn to what people in computer vision have been doing about shape. So this has a long history. So there are ideas which are based on top-down approaches to shape. So if I know what I'm looking at, then that gives me a way to interpret the shape. So since I have seen faces and heads in real life, I've seen thousands, hundreds of thousands of these. Then when I'm given a photograph, because of my previous experience, I can imagine how the shape must be in 3D. So the photograph is just 2D, but my prior experience has been 3D. And that memory enables me to convert that 2D picture into a 3D one. So that's one source of three-dimensionality. The second source of three-dimensionality is related to the fact that there's something in the signal itself. And that can be due to the fact that we have two eyes. So I get slightly different views of the scene, and therefore I can do triangulation and get depth. Or I can get multiple views by just moving around. And these ideas really go back to the Greeks. I mean, 2,000 years ago, Euclid understood the geometry of this process. It's triangulation, right? It's been known for ages. And of course, we had to convert that to a computational form. So these are the ways in which the computer vision community has tackled 3D. Now, and these two traditions were actually quite distinct. There's a top-down tradition and there's a bottom-up tradition, and they were quite separate from each other. What we are trying to do now is trying to unify them in one framework. And the next few minutes, that's going to be perhaps the most technical part of my talk, where I'll give an example of how we can use this deep learning methodology to try to bring together these two traditions. So I'll take a specific problem, which in fact we are going to talk about next week in ECCV. So just to give you a flavor of what this research is about. So here is this image. So you look at this bird. So first you say it's a bird. Okay, good. That's based on past experience. But you know more than that, right? You somehow imagine all this, right? You imagine that there is like a 3D shape of this bird, and you kind of guess what it would look like from some different viewpoints. So we imagine all that. So what enables us to do this? This bird, you only have this flat photograph, right? So you don't know anything about the 3D shape. So it has to be based on our previous experience. So our previous experience of birds that we have seen, right? Now, now that previous experience, so let's try to be more precise about that previous experience. So the previous experience of a bird might be a picture of a bird. You might know, based on recognition, you might be able to identify key points on the bird, that this is the beak, this is the tail, and so forth. And you might be able to identify the silhouette. So this is all two-dimensional reasoning. Okay. What we have is lots and lots of examples like this. We never have a 3D model of a bird. Why? Because I can't grab a bird and put it into my machine, my scanner in my lab. If I could take that bird, I mean, I would have to kill the bird, stuff it up like a taxidermist, and then I could take a model, but I would not be able to get too many models this way, right? I can't take birds and put them into a scanner. So I'd never have access to the ground truth 3D model. All I have access to are multiple pictures of the bird. But there is a catch. The catch is I never have multiple pictures of the same bird. If I have multiple pictures of the same bird, I can use triangulation, right? My left eye sees, my right eye sees, I draw the lines, and then I know the depth. But I don't have that, unfortunately. I don't have multiple pictures of the same bird. I have many, many birds, but just a single picture for each. So how do I resolve this puzzle? Right? That's the thing that I'm trying to say. So what we are trying to do, and this is where the magic of deep learning comes to the rescue, and I'll give you some flavor of it. So what we are trying to do is to actually produce a machine, this function f, which given that single image is going to spit out all these things. It's going to produce the shape, it's going to guess where the camera is, it's going to guess what the texture is. And once you have that, then you can produce a novel view quite easily. So how do I produce? So the challenge is to train this function f, which given a 2D image produces all this. So what we have to do is to train this function f using lots of examples. And the examples are going to be that we are going to have lots and lots of pictures of birds. And we are going to try to guess all of these things like where are the key points, what's the mask, etc., the texture. And what we have to do is we have to bring in some general principles and priors, okay? Because you can't get something out of nothing. I mean, this is something to keep in mind. Learning approaches somehow suggest, oh, you can learn everything, and no, you need to have some prior knowledge. You cannot learn from a completely blank slate, okay? You need to have some basis on which to learn. And here, the kind of basis that comes in is, for example, you can assume that the shape is symmetric, and that the shape is not, it's sort of smooth in some way, and which can be mathematically encoded using ideas from differential geometry and so forth. And again, now I skip the details, okay, but the end result is that just from a collection of 2D pictures and this prior knowledge that shapes are smooth and symmetric, we are able to learn this function which can, given a 2D image, produce the 3D shape of the bird. Okay, and here are some results. And we've taken these ideas and applied them not just to birds but also to humans. Humans are a bit more tricky because humans are articulated and their arms and legs can change. And but here is some result where what we are doing is, here is a video stream, and in this video stream we can detect the human and then replace the human by this 3D shape, and where the person's arms are, where the person's legs are, where is the camera, and so on and so forth. So these are the kinds of things we can do. So now let's look at this image, and then let's see what computer vision can do today. So what computer vision can do today is, or it's getting there, or we can detect people, we can say here's a person, there's an accordion, there's this bench, and we can match that bench to some 3D shape and so on and so forth. Okay, but go back to this picture, and then what is it that you really want to know? Is this what you really care about? So I think as we talk about artificial intelligence in a more general way, we really are after intention, behavior, activities, and so on. So when I look at this picture, to me the interesting question is, okay, I look at this and then I see, okay, this lady, she is a musician. She's playing this accordion. If you look carefully at her feet, there is this bag, and if you look more carefully, you'll see some dollar bills there. So obviously she is playing and expecting people to put in $1 or $2 if they like her music. And I think this guy is standing there and he's trying to decide, should I go off to my, catch the train and not be late for work? Should I put in the money? Should I go away? So these are the kinds of, okay, I'm spinning a story here, but actually some versions of these stories are in fact essential. When we talk about analyzing analysts or intelligence analysts' work, they really have to interpret what is going on. And I gave you some examples of the kinds of interpretations that we as humans make. And that's what we need to get to. Finding out people and their shapes and the bench and its shape and so on is part of the answer, but it is not the complete story. Okay. So therefore, this is like, will person B put some money into person C's tip bag? And this we can't do. So I would say computers today have pitifully low social intelligence, whereas we need to understand the state of humans as they interact with each other in the external world. And there are reasons for why this is difficult. It's because human behavior is in the context of goals, whereas what we can see from the pixels are just low-level patterns of movement. So right now, what am I doing? Am I just moving my hands? Am I giving a talk? All of these are true, right? But the computer currently is focused on the most low-level, mundane aspects, and we need to get to what I would call the hierarchical structure of human behavior, which is that we would need to go from just understanding movement to understanding goals. There are good examples of this. Any situation, how do we understand a situation? It's in the light of previous experience of those situations. This is, of course, not a new insight. This is something which is quite fundamental, and it goes back to someone called Kenneth Craik. He was a British scientist. This is around World War II time period, and he died at an early age in an accident. But he wrote this brilliant statement, which I'll just let you read. So that's what humans are doing when we are interacting with each other. Like, I have a model of you and you have a model of me, and we are communicating through that. What we need is our computer programs need to be able to infer this at this level, okay? Not just that I'm moving my finger, okay? You want to get to the deeper level. We are not there yet, okay? Okay. So let me now sketch a program of research where how do we try to get to this more deeper understanding? And this deeper understanding has to be this embodied intelligence. So I had showed this slide earlier, which was on the phylogeny of intelligence. How did intelligence arise over evolutionary time? But we could equally focus on the ontogeny of intelligence, which means how does intelligence develop in a single individual? Human baby from birth onwards. So we know quite a bit about it, because people in, the area of child development has been the subject of scientific study, and there's quite a lot known in the last 30, 40 years. There have been major developments in that. So I'll just start from the top. So if you look at that baby is exploring the world. So the baby is like hitting at objects, touching them, feeling, hearing the sounds, seeing what happens as a result of the movement, and so on and so forth. So there is one of my colleagues, Alison Gopnik, has a book called The Scientist in the Crib. So the metaphor she tries to evoke is that the child is really a scientist doing experiments with the world, and from that learning, creating hypotheses, and building a model of the external world. And then that child, then on the right is, then that child goes to the zoo with her mother, and then the mother points to the zebra and says, zebra. And then the child knows about zebras with one example. What do our computer programs do? We have to show them one zebra, then another zebra, then another zebra, then another zebra, and with 1,000 examples, finally the neural network does something reasonable. Why? It's because our computer programs are kind of like idiots compared to that child. The child is a genius, right? Because the child has experimented with the world and has this very sophisticated understanding of the physical world, knife physics, etc., etc. So I give the same example when I talk to colleagues who are working on autonomous driving. So in autonomous driving, I mean, this is a big thing now, right? We're going to have self-driving cars any day now. And I am on the more pessimistic side there. And part of my reason is that how do we teach people driving? Okay, it's a 16-year-old high school kid. But that 16-year-old high school kid doesn't start out with a blank slate. For 16 years, he or she has been doing all this other stuff, interacting with the world from which he or she has become a visual genius. And now you just teach them driving. You don't have to teach them about the visual world and the behavior of people. So I know when I'm at a crossing, at a pedestrian crossing, I have to think about things differently from whether it's an old person. I think, oh, they're going to take a long time to cross. Then there's a mother with a child. I have to think, okay, this child might just dart across. I mean, and so on and so forth. Or there's a guy in a suit, and I sort of have an expectation of how he will behave. I have all that coming into the 0.5 seconds where I'm interpreting what to do at the crossing where I'm driving. How are we going to get that, right? I mean, if we can find settings where we don't have to worry about this, for example, in freeway driving, then I think the problem is much easier. But as we make it more and more general open situations, you more or less have to deal with the fact that we have to create systems which have our visual geniuses. Now, there is a style of research which is so Bezat, 10 minutes is okay for me to finish? Okay. So there's a way to pursue this which was outlined by Turing. So Turing in his 1950 paper, which is like the first paper which laid out the prospects of AI, he says this: instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one could obtain the adult brain. So I think that in the early days of, given the computing resources we had 50 years ago, this was not a realistic path to pursue. But today, I think it might be. And I think that, so we can create these visual geniuses. So let me show you a few examples of work along that tradition. So first I want to have this slide. This is from a paper in child development from Linda Smith and Michael Gasser. This is just as a representative of what people in child development, the psychologists who study babies, what have they told us? So they tell us that children are multimodal. So like that baby hitting at some object, you get touch, you get sound, you get vision. Okay. Incremental, so you don't start teaching quantum mechanics to a 2-year-old, right? We have a sequence of learning. First, the informal experimentation that a baby does at home, then they go to school, etc., etc. Physical, there's a lot that you learn from really interacting with the environment. So you're building up a model of the physical world. Explore, be social, we learn from others. It's not just in isolation. And then language, finally, which enables us to acquire models of situations we've never directly experienced. So I emphasize the sensorimotor aspect, but I don't want to say that only that is needed. Language is needed because language considerably broadens what we can acquire beyond our direct experience. So let me give you one or two examples of papers. So this is from our group. So what we decided was, okay, let's try to see if we can make robots learn the way babies learn. So we have this experiment. Let's see if I can launch this. So instead of trying to train the system by hundreds of thousands of examples, like labeled examples like ImageNet, so here we have this robot which is doing experiments. So it's doing experiments like this. It's doing very stupid experiments. The experiments are the robot pokes at some objects, and then there's a camera at the top, and then the camera looks at the image before it does the poke, and then there's an image after. So, but hopefully this reminds you of this, what the baby was doing. And now we collect lots and lots of these examples. But we don't have to do any work. The robot just keeps on doing this. Okay. So now we have these the before situation, the after situation, and what action you performed. So we have now these triplets. So now the system has become self-supervised. We do not need an external annotation. And then there are some details, which is that you process each of them by this is called a so-called Siamese network with two heads. So you train you run each of these images through a network, and then you try to predict the poke. What you try to do is to learn two models. And this is again an interesting idea. One is a forward model, which is like predicting physics. So if there was a certain situation and you performed an action, what would be the result? So that's the forward model. Then there's the inverse model, which is I'm in a certain situation. I want a certain desired situation. What action should I perform? So that's what we have to do to change the world, right? We have to perform actions. And that's what you use for planning. You want to get to a desired state, so what should you do? And it turns out that actually learning them together is very helpful. So don't learn them separately, learn them together. And then here are some examples to show that this actually works. And we tried this in a few other settings, like teaching the computer to tie knots and so forth. This was a pretty hard problem otherwise. And it turns out that if you try to just program this, there are just way too many cases. And you can't build a good, accurate physics model of this. On the other hand, the robot can do lots of experiments. So it picks up the rope at one place, drops it, picks up the rope at another place, drops it. So from that, it builds up a model, and then it can plan. We've used these ideas for learning image segmentation. How do I? So very important is that the world is composed of objects or people. It's not just one set of pixels. It's really composed of these separate entities. And some are passive like objects, and some are active like humans. And they have they move, and they have goals and so on. How do we acquire that knowledge? So we decided that instead of training a system with examples, the system should acquire its own examples. So this robot is going to build up a segmentation system by trying to pick up objects, and so it might poke in this at the background, and then it doesn't have an object. So that would be a failure. Or it could pick up an object. By doing a lot of those experiments, it acquires the concept of an object. And I'm going to skip all the details of this in the interest of time. And it turns out that this active learning actually operates much faster than passive learning, which is what is traditional with lots of examples. And then we can do some object okay, in the remaining 5 minutes, I want to give you another flavor of how perception and action can be combined. And this is in the context of navigation. So we have a robot in some environment, and we want it to learn to navigate. So this is obviously a very important problem. This is navigation, right? And now the challenge here is that it may sometimes be in environments of which you have only very partial knowledge. If you have a complete map of the situation, that's a different version of the problem. I'm talking about the settings where you acquire your map as you go along. So robot navigation in unknown environments. Now, the robotics community has been tackling this problem for the last 30 years, but the way they've done this is that they've broken it up into two stages, where the first stage is complete mapping, 3D reconstruction. So and then the second stage is that you try to find a path. So this is classical mapping and planning. The first, what you do is you build a 3D map. So let me tell you how extreme and in a certain sense ridiculous that approach is. So if I want to move around in this room, I would need to, first the robot would need to go everywhere, take lots of pictures and build up a complete map. So you would need to have a map of every chair in the room, every person in the room, every briefcase on the floor. Okay, all this so that you just can figure out a path from how do I get out of this room. Right? Now, clearly, we as humans do not require that knowledge. And expecting this stage, advanced stage of map building is really way too much. It really should not be necessary. Okay. And you're actually not making use of partial knowledge which can be helpful. For example, that when you go out of a corridor, of a door, you're probably going to be in a corridor. We have a sense of what exits look like, etc., etc. So instead, what we did was we converted this problem into one where we make use of we have a mapping stage, but the mapping is kind of just absorbing information. You have a certain image, and then as you move, you absorb that into your current data structure, if you will, and then you use that for planning, and then you train this end to end. And then I'm skipping a lot of the details, and it turns out that we can. And here are some tests in real environments of this approach. So the basic idea is you do not need to build a complete map. You just build a partial map based on your observations. And it's not even a map per se, it's just the partial information you have. And then that is enough for planning. What you do is you train yourself to do this task repeatedly, and that's how you become an expert in moving around in new places. And we show some numbers, which I'll skip. Here is what we've been doing more recently. I'm quite fascinated by how animals navigate. And animals are amazing. They're birds who navigate practically from like the North Pole to the South Pole, right? And fish, and how do they do it? They do not have access to the complete map. There's a lot known about how they use landmarks, for example. So they use a combination of mapping and landmarks. So my version of the problem is when I come to a new city, the first time round I use Google Maps and I plot a path. But the next time round I don't use Google Maps. I sort of remember, okay, after I've gone like 2 or 3 blocks, then I see the Starbucks, and then I turn right. And then I see this tall building, and then I turn left, and so on. So that's how humans remember paths that they have traveled. And I'm sure that our sort of hunter-gatherer predecessors, for them it was even much more important, right? It was a matter of living life or death. So we need to have a way of using these visual landmarks. And so we've developed sort of these techniques where your experience is recorded as a series of visual landmarks. And in fact, it gives you a lot of robustness, because if there are some cars on the street which have moved, it doesn't matter. Whereas if you had a detailed map, that would have become obsolete. And so it turns out that this is taking inspiration from biology here is very useful. I want to conclude with a direction in which a lot of this research is going. We need to create in the computer very, very accurate simulations of the real world, so we can then program our agents operating in this. And again, given the technology that we have now, because we now have very good ability to scan real-world environments, we can now create in the computer copies of these environments in which we can try out our approaches. And this is, I think, and these models can be accurate enough, not just in terms of the geometry, but also in terms of physics. So you can do very, very, so your intelligence could emerge in these simulated environments. So that remains to be seen, but I'll conclude here with my view of how intelligence has to be. It's not in isolation. Intelligence is perception, action, as well as language working together. Thank you very much.